I'm a software engineer at Lawrence Livermore Laboratory, and I've been working with a team on a brain imaging workflow that uses probabilistic tractography, and I'll explain what that is in a bit. So we've been using Parsl as our main supercomputing process orchestrator. So our goal is to convert these MRI images into what is known as a connectome, which is kind of like a mapping of the different regions of the brain in a way that's very tractable to matrix analysis. So this is a very expensive process. This is something that previously neuroimaging researchers would spend hours or days processing on individual computers. So moving it onto supercomputing platforms is something that is very much anticipated by our collaborators. So the way this algorithm translates into a Parsl process, it uses Parsl's ability to handle heterogeneous resources by allocating some jobs to GPUs, some jobs to CPU-only nodes, and sometimes dividing and splitting nodes or splitting tasks as required across different nodes to maximize resource usage. So this presentation is called a Memory-Unsafe Processes with Parsl. And the reason is because this is kind of a unusual situation in that one of our applications called ProbTrackX, it's kind of a monolithic application. It's a binary, it's pretty opaque. I mean, the source code is open source, but when we do run it, it does seem to overrun a lot of the memory safeguards in place, at least on our Unix systems. So what this means is that if you run it on an individual machine, it will run as you expect. If you give it a machine with like 32 gigabytes of memory, it will allocate that much memory to each task it's trying to process. And this is great for running it individually, but if you want to run it in parallel with Parsl, then we're going to be running many examples of ProbTrackX, oftentimes on the same node. So in a normal application, we would want that node to share memory between all of those processes. So for example, in this diagram on the right, we have all of these edges, and each edge will run a ProbTrackX process. So each edge might consume gigabytes of memory simultaneously. And whereas a normal application, we would expect memory overruns to simply go into paging, and that wouldn't be an issue at all. For whatever reason, ProbTrackX doesn't respect that. So when we try and run many edges simultaneously on a single node ProbTrackX, we get memory overruns and segmentation faults, and it's very ugly. And we've tried very many ways to handle this through more, I guess, formal, more well-established methods. Parsl does have a way to limit process memory usage. And this is great if you know exactly how much memory each process is going to use. But unfortunately, the actual size of each data file within each edge can be variable. So we need a way to handle varying amounts of memory in each process during runtime, and then be able to safely handle that between parallel processes so that no individual process overruns the current memory budget. So again, this is a very kind of niche problem, but it's one that we had to devote significant time to tackling because we have to use this ProbTrackX binary application. So the way we handle that is by creating this memory record that is shared between multiple processes on each individual node. And what we essentially do is each edge will contribute to the memory record and saying, I'm using this amount of memory. And this memory record has to be process parallel safe. We use Unix file locking to ensure that whenever you're accessing this memory record, it will be the latest data across all parallel nodes, and it'll be completely atomic and parallel safe. So once we're able to ascertain that we have enough memory to run our edge, then we'll add that to the memory record and continue running. And once that edge is complete, then it'll read back into the memory record and free that memory. This is a rough way of doing it because we have to estimate the amount of memory our process is going to use from the beginning of running that edge. But it's the best way we found to ensure that we're A, using memory as efficiently as possible on each individual node, and B, never running the risk of getting a memory overrun and a segmentation fault within that node. So the actual way we do it is by simply sleeping around until we see that the shared memory record has enough free memory. So obviously this approach is kind of ad hoc. There are limitations. First of all, it shouldn't be used at all in the first place. Like these memory unsafe applications, like this should be handled upstream within the application itself, but assuming that's not possible, then this is something that you'll have to do. So there are incompatibilities. The file locking is sometimes doesn't have consistent behavior across Unix systems, and that can lead to issues where if the file locking on the memory record is not respected, then it will lead to the memory overruns that we had in the first place. And also we have to be able to estimate the amount of memory used in each process. And that's sometimes hard to do correctly. So say that you're loading a large chunk of memory. What if your application only loads like chunks of that at a time? Then that's not being captured by your memory estimate. So this can waste resources if you're using a worst case scenario like we are. So this is just a kind of, I guess, presentation of the kind of, I hesitate to use the word hacky implementation we used to get our Parsl workflow running. But if anybody has similar experiences or has a better solution, then well, that's something that we're obviously interested in. But this is just our way of handling this issue.
I have a suggestion.
Okay, go for it.
So Kubernetes was kind of designed for this exact type of case where you submit jobs with requests and limits, which are a window between the minimum and maximum memory you expect to run. And when it overassigns the node, and then when one process segfaults, it preserves the runtime in the container and transmits it to another node and resumes computation where memory is available on the grid. And it's quite literally designed for this exact scenario. So I think and it's called an eviction. So a Kubernetes eviction was designed for this exact type of unsafety, and Parsl provides Kubernetes providers. So looking into configuring the nodes with that engine would be like the non-hacky way of doing this.
Okay, so in Kubernetes, is it pretty straightforward to like
no
job on an individual like node level or on individual system level? Because
no, it requires that there's like at least 4 or 5 nodes to resume the unsafe practice. Otherwise, there's just no way to do it.
I see, and it assumes you have heterogeneous resources already. Like there's certain nodes that have extra memory.
Well, Parsl has that capability too if you use the workflow executor. But yeah, it is for heterogeneous. It can work with a heterogeneous system of nodes. So yeah, you could have like 2 or 3 with like a 250 sig RAM kit and a 32 and a 16, and it will safely complete the problem you described.
Okay, suppose that the node, each of the nodes are like monolithic. They have the same amount of memory. Would an eviction move a process onto another node of the same type, and like that wouldn't cause any problems?
It would try to. That's the way the scheduler works, is to to determinately overschedule a node and then it's like a fluid basin basically. Yeah, it floods a node and then pours the rest with evictions to make it as computationally efficient as possible. That's why Kubernetes is used for cloud processes. So yeah, that I think it's definitely something to look into.
Okay, definitely. Yeah, I appreciate that.
And I've heard murmurings from people at Livermore about deploying Kubernetes clusters there. So Joseph, I'm not sure if you have access to one or if one exists, but they certainly talk about it.
Yeah, it's something that they've worked on some pilot nodes. I'm afraid the workhorse clusters I'm using right now doesn't have Kubernetes capability, but it's definitely something that the lab is interested in.
Yeah, just quickly, someone more knowledgeable than me, perhaps Ben or Yadu, would the work queue executor help in this case with its ability to dynamically size based on what it sees for memory usage? Or Doug or Ben? I think Ben Tovar's here. Someone could just nod or shake their head or shrug.
So my use of the work queue stuff has been that you need to know ahead of time how much you're going to want to allocate, rather than anything dynamic happening as a run proceeds.
Okay, it might be worth having, oh, sorry, whoever that was, but might be worth coming to Doug Thane's talk, which I believe tomorrow, Joseph, is around 2 something, which will talk a little bit about resource management and the work queue executor, and potentially we can ask him if there's a good solution.
Yeah, that'd be great.